All right, let's go ahead and get started. I do want to welcome you to this worksheet. This is Lewis Structures. You are going to need a periodic table for this one, so if you don't have one handy, go ahead and pause the video and we'll get started. So here we go. Lewis dot structures. What we want to do now is draw the Lewis dot symbols for the following elements. What do we mean by Lewis dot structure? What we mean is a symbol together with the valence electrons or as they are arranged around the atom. So for example, carbon has the symbol carbon, obviously C for carbon, and we're going to note that carbon is in the 14th column and therefore has 4 valence electrons. We're going to place those 4 valence electrons at opposite ends of the symbol, so we have no pairing of electrons in this carbon atom. Next is sodium. Sodium is on the left-hand side of the periodic table. It has this symbol right here, and it has a single valence electron, so I'll place that on the right-hand side. Could have done it on the left or top or bottom. It really doesn't matter as long as it's by itself. Aluminum is on the other side of the transition metals. It is a L, just like that, and it's going to have 13. It's in the 13th column, so we'll have 3 valence electrons. I'll put one there, one there, one there, and so that's 3 valence electrons for aluminum. That's how I draw its Lewis structure. Bromine is a halogen. It has this symbol, Br, and it has 7 valence electrons. I'm going to keep these electrons as far away from each other as possible for as long as possible. So 4 valence electrons, push them out as far as I possibly can, and then what I'll do is I'll put the next 3 in. So that'll give me a total of 7 valence electrons around the bromine. Notice that this electron is by itself. Phosphorus, 5 valence electrons. It's in the 15th column. It has a symbol of P. So I'm going to say 1, 2, 3, 4, 5 valence electrons, just like that. Notice the 3 unpaired electrons and the 1 pair of electron up on top. Krypton is one of the noble gases. That means it's going to have an octet of electrons around it. It's not going to be susceptible or not going to want to bond with anything else because it has the magic number of electrons around it, 8 valence electrons. All right, let's move on. Lewis structures, we said, were the structures which allow us to see the electrons' proximity to certain atoms or how they're arranged around a certain molecule. So we're going to start with HF, or hydrogen fluoride. So a Lewis structure is a structure, again, that tells us where those electrons are. How do we write a Lewis structure? Well, let's start with a couple of rules. The first thing we want to do is we want to determine the total number of electrons available in the structure. So we want to just add up valence electrons. We don't care where they came from. We just want to total them up so we know how many to put in the structure. The next thing is we want to use the electrons, use a bonding to pair electrons when appropriate, and then we'll use any remaining electrons to complete octets, or in the case of hydrogen, hydrogen needs 2 electrons, not 8. So let's start with this one right here, HF, hydrogen fluoride. So hydrogen, you know, has 1 valence electron, and fluorine has 7 valence electrons because it's in the 7th column. So we have a total of 8 electrons. Now, 8 electrons have to be distributed in this Lewis structure. So let's just start with the simplest way we can draw the structure with an H here and an F there, and then let's put a bond right there. By putting that bond there, we use 2 of the 8 electrons. So that means we have 6 remaining. Where do we put them? Well, we're going to put them around the fluorine. 2 here, 2 here, 2 here, and 2 there, just like that. That uses up the 8 total valence electrons and completes the structure because hydrogen feels as though it has 2 electrons in this bond, and fluorine feels as though it has 2, 4, 6, 8, and 8 electrons surrounding it. So it's a reasonable structure. Let's go to number 8. We have CH4. This is called methane. So let's add up valence electrons. Carbon has 4. Each of the hydrogens has 1, but there are 4 of them. So we're going to say 4 times 1, that's 4. So when we add 4 to 4, we get a total of 8 electrons. Let's put them on this structure. So we're going to have carbon here, hydrogen there, hydrogen there, hydrogen there, and hydrogen there. We're going to use bonds to connect the skeleton. Here, 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 and here. 2, 4, 6, 8. Well, that's all of the electrons that we have. Is everybody happy? This hydrogen has 2, 2, 2, 2. The hydrogens are happy. How about the carbon? Remember, in each bond, there's 2 atoms, or 2 electrons, so 2, 4, 6, 8. And now the carbon's happy as well. That's a reasonable structure for methane, and we'll move on to number 9. Number 9 is similar. It's not carbon CH4, but rather CF4, but it's done similarly. Remember that carbon had 4 valence electrons, so I'll add those in right there. Each of the fluorines has 4, but there are, or excuse me, 7, but there are 4 of them. 4 times 7 is 28. So how many do I have total? 4 plus 28. I've got 32 valence electrons total. So what I'm going to do now is I'm going to arrange them just like this. Carbon here, I'll put a fluorine here, fluorine there, and a fluorine there. So now we're going to use these bonds to connect these just like that. So 2, 4, 6, 8. So of the 32, I've used 8. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, and that is my structure for carbon tetrafluoride. Okay? Let's go to number 10. We've got ammonia, NH3. Nitrogen has 5 valence electrons. It's in the 15th column. And hydrogen has 1, but there are 3 of them. So 3 times 1, obviously 3. 5 plus 3, that's a total of 8 electrons. Let's put them in. Nitrogen here, and I'm going to use these bonds just to connect hydrogens. So that's 2, 4, 6 electrons just to connect hydrogens to nitrogen. Where do I put the other 2 electrons? I'm going to place them right here, one there and right there. And now everybody's happy. The hydrogens have 2 electrons each, and then nitrogen has 2, 4, 6, 8. 2 of them are lone pairs, and that's going to affect the geometry, but I'm not concerned about that right now. I just want to know the Lewis structure and where those electrons fit in. So it looks, for ammonia, it looks like that's going to be the structure. Let's look at O2, number 11. Number 11 has oxygen gas. Remember, the oxygen is in the 16th column, so we're going to say oxygen is 6 times 2, right? So oxygen 6 times 2, so obviously 12 electrons. Now let's take a look at what's going to happen if I try to do this with a single bond. I'm going to put a single bond between the oxygens, just like that. Now 2 of the 12 electrons have been used, so let's do the others. So 2, 4, 6, 8, 10, and you notice I've run out of electrons. This oxygen doesn't feel as though it has 8 electrons. So that's not a correct structure, right? That's not a correct structure. When I run out of electrons, the correct procedure to do is to try double bonds, and that's what's going to happen here. I'm going to say a double bond between oxygen. These 2 oxygens right here will have a double bond between them. Remember that each one of these bonds has 2 valence electrons. So 2 here, 2 here. That's a total of 4. So I need to account for the other 8. I'll put them right here. 2, 4, 6, 8. Let's check this and see if it's correct. So each of the oxygens, 2, 4, 6, 8, 2, 4, 6, 8. That looks like it's a reasonable structure. Notice that oxygen gas has a double bond. CO2 and the next one, number 12, is very similar to this. Carbon again has 4 valence electrons. Each of the oxygens have 2. So that's 2 times 6. That's a total of 12. That's 16 electrons. So 16 electrons. As it turns out, the best way to arrange those 16 electrons is like this. I'm going to have double bonds on either side of the carbon, and then that's 2, 4, 6, 8, 10, 12, 14, 16 electrons. Oxygen's happy here. Oxygen's happy here. Carbon has 8 electrons around it as well. Everybody's happy. We're going to move on to number 13 now. Let's look at number 13. We've got SO4 2-. This one's interesting. It's a polyatomic ion. Sulfur has 6 valence electrons, and each of the oxygens have 4. So 4 times 6, obviously 24. So we've got, so far, 6 plus 24, we've got 30 electrons. But notice that this is a polyatomic ion having a charge of -2. That means that there is an additional 2 electrons that we have to account for. So we've got 6 plus 24, that's 32 total electrons that we must account for. So let's do that. We're going to put sulfur right here. We're going to put an oxygen here, oxygen there, and there. We're going to connect these with a bond, 1 to each of the oxygens. So now we've got 2, 4, 6, 8 of the electrons of the 32 accounted for. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 electrons. It is a polyatomic ion, so to kind of keep things nice and clean, I'm going to put a bracket and put a little charge of 2- right there. That completes my structure for SO4 2-, the polyatomic ion. Now we've got nitrogen gas, N2. Now nitrogen has 5 valence electrons. There's 2 of them, so 2 times 5, obviously 10, right? But if I try a single bond, won't work. Try a double bond, won't work. There's not enough electrons. Remember, if you don't have enough electrons, try a double bond, and if you still don't have enough electrons, try a triple bond. That's going to work here. So we have a nitrogen here and a nitrogen here. 1, 2, 3 bonds between those. That's 2, 4, 6, 8, 10. The Lewis structure for nitrogen gas has a triple bond. Don't forget that, by the way. That's a triple bond between the 2 nitrogens for nitrogen gas, and we're done with number 14. Let's move on to the advanced questions now for honor students. We've got NO3 minus. Now, a reasonable structure for NO3 minus is this right here. It's going to be a nitrogen double bonded to oxygen, just like this, and then another oxygen, and then another oxygen, and there will be 2, 4, 6, 8 electrons there, 2, 4, 6, 8 electrons right there, and we'll put a negative sign right here, and that would be a very reasonable structure for this compound. But the question would be, why the double bond here? Why couldn't it have been here? So somebody else may say, well, it could have been there. So I'm going to do this. I'm going to put a nitrogen here. I'm going to put this oxygen here and put 2, 4, 6 electrons around there. I'm going to have an oxygen here, two pairs of electrons there, and then I'm going to have this right here, 2, 4, 6 electrons, just like that. And then I'm going to put the negative sign right here. And then I'm going to ask myself the question, well, that's possible, that looks good, but why couldn't it have been this? Why couldn't it have been the nitrogen in the center, just like that, and the double bond on this oxygen with this like this? Why isn't this possible? And the answer is, it's very possible, right? There's nothing wrong with that. And so the point is this. The point is that we've created a structure. We've created something that is called a resonant structure, right? By the way, I'm going to tell you what. I'm going to put the negative signs all in the same place. I'm going to put them all in the upper right-hand corner. So I'll put it here, here, and here. So these are called resonant structures. And we're going to draw these double-headed arrows just like this between these structures, just like that. And resonant structures then indicate the fact that we see in this NO3 minus a kind of an overlap of structures. In other words, it's like this some of the time, it's like this some of the time, it's like this some of the time. And some people believe that it's actually all 3 simultaneously, right? In fact, that's probably closer to the truth, that this structure, and this structure, these so-called resonant structures, let me write that right here. These resonant structures are present, they morph into each other just like that. Okay, and the last structure is SF6. The reason I put this one on here is I wanted you to understand that there are certain compounds that are exceptions to the octet rule, and this is one of them. So sulfur hexafluoride is this one right here. There's a fluorine also down here, is an exception to the octet rule. I just want you to remember that it is an exception. That's it. That's all I want you to know, is that there are some compounds that do not follow the octet rule. Here we have, instead of having 8 electrons around the sulfur, we have 2, 4, 6, 8, 10. We have multiple bonds, too many electrons around the sulfur, but it is an exception to the octet rule, and we'll just keep that in mind. Folks, I'll see you on the next one. Thank you. Bye-bye.